This series has been a fantastic success. Basically, we are very, very pleased with the outcome, and I believe that you will like today's webinar. It's a little bit extensive, but it's very detailed, and we put a lot of effort into it. So today we will basically discuss how to dimension and optimize LTE parameters, what needs to be done. There is a lot of material that we are providing. We will cover a lot of it, but some slides are for support for you to see how they are, for you to follow up the presentations and so on. I will close the camera so you don't need to be staring at me. Okay, my name is Leonard Korovajchuk. I am CEO and CTO of CelPlan International. 45 years working in the R&D in telecom field, several patents, and basically here we have published 2 books, one about CDMA, the second one about LTE and WiMAX and WLAN, and now we are writing the second edition of this book. Should be published next year, beginning of next year. It probably will have more than 1,000 pages already. Then we are also writing a book about network video, wireless backhaul, and multi-technology networks. And in the plans are smart grid networks also. A little bit just very briefly about our company, CelPlan International. We are headquartered here in the US, more than 500 employees today. More than 20 years in business. We are an employee-owned company, and we have subsidiaries in 6 countries in the world and growing. We are totally vendor independent, and we provide network design software. That is our CelPlan suite, and the new products are designer. And we do a lot of optimizations, and part of what, not part actually, everything you will see today in the presentation came from the specifications that we do for our tool to be able to simulate the existing networks, and also from field experience, from optimization experience that we gather in the field. So this is, I am the presenter, but this is a group effort that everybody that works in the company contributes, and I think we have been very thorough, very successful in what we do. This is part of a webinar series that we devised in the beginning of the year, and we already gave 4 webinars, very great success. Actually, we are very surprised with the number of attendees and so on. For this webinar, we have more than 500 registrations, and the number of countries is also growing. And we have still today's webinar, and then we have another 2 webinars in before the end of the year. So, and one webinar is building on top of the other, so you can always see them in our website on in your YouTube. Our first webinar was how to dimension user traffic in 4G networks. We have participants from 44 countries, and the YouTube views last week were at 572, so probably now it's even much larger. Very important what we have done in this webinar was to establish user traffic, and you will see that today we will use a lot of what was discussed in this first webinar. So how to dimension user traffic, how to characterize data speed considerations, and the most important thing is that we were able to define per user type what is the traffic, what is the average packet size that is very, very important for dimensioning, and so on. So there are several parameters that we have added, we were able to extract to characterize user traffic. From when we gave them in this webinar to today, the only addition we did, as far as I remember, is the services that have semi-permanent scheduling, SPS. But this is minor, and probably next year we will introduce this in the webinar also. Then the second webinar was in June 2014, how to consider overhead. Very, very important, and how to dimension the overhead. 49 countries, 285 views, and that's not, it's not counting people that download directly from our website. Basically, in this case, we calculate what is the amount of overhead that we will have in the LTE cell. You will see that this overhead can be overwhelming, can be 40, 50, 60% of the capacity. So it's very important that this is properly dimensioned, and that's what we did in this webinar. We explain about the construction of the frames, the cellular reuse, and so on, and then we explain all the overheads, or the major overheads, and we showed you the capacity calculator. On webinar 3 in July, we spoke about customer experience and how to consider it. We had 40 countries. We already have 230 views. In this webinar, we spoke about how to evaluate customer experience, what factors are affected, what are the parameters, and of course, customer experience is greatly dependent of the signal to interference and noise ratio, and we gave some innovative methods of considering these, of calculating, and so on. In webinar 4, we spoke about LTE measurements, what they mean, how they are used, and this was again 44 countries, 245 YouTube views. And it was a very extensive webinar also, where we spoke about network measurements, field measurements, and we gave the main measurements specified by 3GPP in terms of UE, in terms of cells, and also how they were reported, what was the frequency, and what was the format of the reporting. Then we spoke about 1D measurements. That is basically what people are used to, but we introduced 2D measurements and 3D measurements supported in our cell spectrum tool. So what are the next events? Webinar 6 is the next one. It will be in October. Registration is already open. And we will speak here of analyzing, wideband channels like the LTE channel. It will be a very, very interesting webinar. This is here. You can see the topics of this webinar and all the different measurements that we are able to perform. It's much more difficult to characterize a wideband channel like LTE because it is in reality a sum of many channels, so it's something that is very, very challenging and requires different approaches, new approaches, and so on. Besides this, we will have in September now the 4G Technologies Bootcamp here in Reston, September 16 to 20. And here is you can see this in the website. I will not go in details, but here are the topics that we will cover. Then we have the Network Design and Optimization Bootcamp that will be on December 8 to 12 at the University in West Indies in Trinidad and Tobago. This will be a very, very extensive webinar, very in-depth, because we are working with the West Indies University already for more than a year, and I am very glad to announce that several other universities are joining us in our program, adopting our software in the classes and also our training material. And this is the topics of this webinar. I also will not go in much details, but you can see it in our website. So please feel free to look at it, and the registration is also open. So finally, let's go to our feature presentation, like in the movies, okay? So today's webinar we will cover what LTE parameters need to be dimensioned and optimized. Here are the contents, and I would like to go a little bit for you to understand what is the structure of this webinar and what we'll be covering. So we will start with a very brief LTE refresher, where we speak about user traffic, overhead, So a lot of this was already covered in the previous webinars, but I need this as a refresher because it will, today's webinar will be based on this as a base, so that's why we introduced this. Then we have network planning. So we will start planning network parameters like BTS and cell IDs, link budget, channel resource assignment, very, very important strategy. What strategy we should use, in terms of planning our resources, neighborhood, tracking areas, and tools that you can use to do this. Then we already, after speaking about network planning, we will speak about the downlink. And then we will have PCI planning, that is one of the most important items. And then we have several parameters that need dimensioned. Need to be dimensioned. We are not covering here, it's impossible to cover in this short time all the parameters. So we choose the most important ones and we'll give you some guidance about other parameters, but there are of course hundreds of parameters that have to be planned and dimensioned. But those, I would say that we are covering the bulk of the, not the bulk, but we are covering all the important ones, although everything is important. Then we will speak a little bit about traffic allocation, and then we will go to the uplink. So downlink will be first, then followed by uplink, and you will see that there are things very, very complex like the random access. The random access, you will see that is really something that you need to understand. We opted not just to give you, a rule of the thumbs of how to optimize, because what we feel is that if we give you just the rule of thumb, that's what people will follow. But in reality, you need to understand whys and how, and so because every situation is different. We don't know of two networks that we can use the same exact solution between them. We have to analyze, and it depends a lot of the network. So it's very, very important that you understand why each one of those parameters was chosen, why 3GPP decided to do one way or another, what are the limitations, and what are the possibilities. After the random access, we will speak about control and data. And finally, we will speak about resource optimization in general. And here you will see that we will be presenting some very innovative concepts that are not even in the literature. So let's start with the first part, LTE refresher. I apologize, I'm rushing a little bit. We have 282 slides to present, so it's really a lot of material, but I strongly believe you will like. So in the LTE refresher, we will speak about user traffic prediction. This was covered in webinar 1. It will be one slide or two, just as a refresher. Then we'll speak about overhead predictions, also in webinar 2. Downlink frame, uplink frame, Zadoff-Chu sequences, orthogonality, and how to consider interference, that was in webinar 3. So let's start with user traffic. If you look at the user traffic predictions, basically what we tried to characterize in the first webinar was that, well, each user will use some applications, and we listed the main applications here. And at the same time, you will have a certain number of users that will use smartphones, tablets, USB modems, or desktop modems, or like MiFis and so on, with a certain number of quantities of those terminals, of those UEs. So this allows us to dimension, based on daily usage, to dimension what will be the traffic expectation of each type of user. And you can classify users as professional, commercial, students, households, and so on. So this is very, very important, but you have here a possibility of checking this against the plans that you are selling, the tonnage, that monthly tonnage that users sign for. So basically, if you have users signing, for 2 GB per month, most probably they will be using between 1.5 and 2, and that's what needs to be reflected here for each kind of user or each type and so on and so on. Then we spoke, we need to speak about overhead. That was, I think, webinar 2. And in this screen is the screen that we finalized in the webinar, where we show, you know, all the different components that we need to consider, all the different factors and so on that will really result in what we show here, that is the availability, suppose here, for control. So after considering all those limitations, our conclusion in this example was that we could accommodate 41 users based on control, but we can only accommodate 10 users based on traffic. Now, what happens is that depending on the mix of services, if you increase services that have very small packets like VoIP and text and so on, this can reverse. So in reality here we are analyzing where will be your main bottleneck, considering uplink, downlink, and so on. So it's very, very important to understand that there is several bottlenecks in LTE, and each one of them has to be analyzed. Let's speak a little bit about downlink frame as a refresher. A lot of you, or I would say nearly all of you, already know this, but basically what I want to refresh is a frame has 1 millisecond. This is the one of the few round numbers in LTE, very easy to remember. There is 1,000 frames per second, and basically a frame is divided in 10 subframes. And a subframe is what we call a TTI, transmission time interval. What this means is that everything is scheduled within a TTI. So in the TTI you have one area here depicted in yellow, and this area carries the mapping, carries the information where in the remaining of the TTI the data is placed and to whom it is directed to. So basically all the mapping is for one TTI, and all the data mapped is sent inside the TTI. The next TTI starts from scratch again, and so on and so on and so on. So you have 10 TTIs per frame. Now, the mapping is not only done for the downlink, it's also done for the uplink, because in the yellow area the eNodeB specifies what should be sent by the UE in the uplink 4 frames later. So the UE will get this information. Oh, okay, I have this slot to send, and it waits the 4 frames and it sends it there then. So basically it's very, very important to understand this, that the concept of TTI, the concept that the mapping is done by the eNodeB for the uplink and downlink, and of course the data of the downlink is sent in the same TTI, but the data in the uplink will be sent 4 TTIs later. Another thing is that is in this yellow area also the eNodeB sends the acknowledgements of the messages received from the UE. And you will see that in the uplink the UE will send acknowledgements for messages received from the eNodeB. Here it's a little bit more of a zoom. Here we have a TTI again. So it's this square, rectangle here, not square. Here are the frequencies, and here is time. Here we have the symbols. So depending if it's normal prefix or is extended prefix, you have 12 or 14 symbols. And what we call control area, where the mapping is, it's from 1 to 3 symbols basically. And here we give the details or timings and so on, so you can look on this with your time and analyze it. And then we have here one area that is where we put the synchronization signals. Everything is based on those synchronization signals. All the timing is based on those synchronization signals. They are repeated twice in a frame. Okay, and those synchronization signals then are used to read all the other messages, to establish the timing for all the other messages. The orange area here also gives some basic information about the structure of the frame. And this is something unique to LTE, because basically what it happens is that this area here has 1.05 megahertz. And in this area, so when we are searching for a channel, we'll only look at 1.05 megahertz to be able to figure out the main characteristics of the channel. We can then synchronize to it. We can figure out, how many control symbols it has, and a lot of those informations. We can, we can figure out the bandwidth and some other basic information that allows us then to read the frame. So we only need to read the central area. But this central area is essential, because if this is read wrong, everything else will be not understandable. Then we can talk a little bit about the uplink frame. The uplink frame is very, very similar in terms of organization. It has the same dimensions. It has 10 sub-frames. A frame is also 1 millisecond, and so on. But the contents, it also has what we call a TTI here. So this TTI here, it is programmed. DNB tells what should be in this TTI 4 subframes before. But the contents of those TTIs are different. You will see that we have what is called a random area, and we have a control area here that, of course, the control area here doesn't have the mapping, but it has the acknowledgements, and it has measurements and quality indications. So that's basically the organization. But it's very, very similar. It's also TTI. It is also the same number of subcarriers, subframes, and so on and so on. Here it's a zoom. And basically what we show here is that we have a same guard band. The only thing that is very important to understand is that this frame is assembled at the ENB. So the UEs have to arrive at the ENB at the right moment. And this means that because there is a propagation time between the UE and the ENB, each UE will have to adjust in timing. So you suppose this UE here that sends this orange part will arrive exactly at this moment, and this other UE that will be in a different area of the cell, it will arrive at this moment in this frequency. So frequencies is easy. The problem is to arrive at the right moment. To do this, there is a whole area called the random access area, and that is specified. It is not in a standard location, so this has to be read by the UE to find out where this area is, how frequently it is available, and so on and so on. And it's a random access area, so the UEs will do a random access, and there may be conflicts. There are orthogonal codes, so many UEs can participate at the same time. But and in this area, we will see that 3GPP had to use different criteria than the regular criteria of 15 kilohertz subcarrier spacing. Now here we compare the two frames, the downlink frame on the left-hand side and the uplink frame on the right-hand side. And you can see that the structure is very similar. It's the same size frame. The concept of transmit time interval is the same, and so on. Here on the top we show the downlink frame, and in the bottom we show the uplink frame. So what happens here is that you can see that the frames are synchronized, but they have a delay of 4 subframes. Okay, so 0.4 milliseconds. And that allows the downlink to send a mapping information here, and this mapping information then is applied by the UE. One of the characteristics of the LTE, of the 3GPP specification, is that the UE cannot request a certain amount of data to be sent. This is calculated always by the ENB. So the only thing UE can do is to tell the ENB is, I have data to send, and there is one more indication that it does indirectly through a regular MAC message where it says the size of its data buffer. So it's up to the ENB to analyze and look how much data is there in the UE buffer, and then based on this it will allocate the required number of resources. One thing that I also would like to tell you about is Zadoff-Chu sequences. You guys are very familiar already with CDMA technology in CDMA 2000 or in UMTS and so on. And basically what you have there is orthogonal codes that allow you to mix several users and then extract the content of each one, because they are combined with the information is carried by orthogonal codes. Zadoff-Chu are a kind of orthogonal codes, but because of the OFDM characteristics, they have a very special characteristic, that is all the modulations, all the symbols are modulated with a constant amplitude in the complex plane. And with this, it's possible to minimize the Papra effect. Basically, the Zadoff-Chu sequences, they are constant amplitude, zero autocorrelation codes, and it allows you to generate several codes or groups of codes. Those group of codes, they are not fully orthogonal to each other, but the main characteristic, the most important characteristic, is that one code of a certain length is orthogonal to its shifts. So each time we shift a code, all those shifts will be orthogonal between themselves. And this allows us to explore this property to send information from multiple UEs and be able to extract them separately. A little bit of orthogonality. People ask, what is orthogonality? What are you talking about? Well, the most important thing about orthogonality is that there is no dependence between two codes or two vectors and so on. A typical example of two orthogonal waveforms is the sine and the cosine, because you will see that the sine is will appear on, the cosine will appear on the x-axis, the sine in the y-axis, and of course you will have a vector here. But this vector, basically, there is no, you can change the cosine and the sine will not move. So that's what is very, very important then, is that the two signals are orthogonal, two waveforms are orthogonal, and this is the basis of OFDM. So and this orthogonality is denoted by this symbol here, orthogonal. And basically, the way it is done in mathematics is through the dot product. All the OFDM is basically based on the dot product, and we will show you some examples of this dot product, because basically algebraically is the sum of the products of all the samples of two sequence of numbers. So we sum the products and then we see what happens. Geometrically is the product of the Euclidean magnitudes of two vectors and the cosine of the angle between them. And the reason that the name dot product is used is because it is derived from the center dot that is used to designate this kind of operation. So basically, as I said, the geometric interpretation is the angle between the two vectors. When this angle becomes 90 degrees, we can say that the two vectors are orthogonal to each other. But they can be rotated, okay? And this is used mainly in MIMO. You will see that MIMO uses this property to extract the signals. Here I have a dot product example. Basically what I did here is to simulate OFDM symbol. So I have here several angles spaced by 7.5, 22.5, 37.5. Then I have the radians here. Just transform the angles into radians. And then I have my I have 5 subcarriers. In this case, I only used 4 subcarriers, so I just didn't modulate nothing in the subcarriers. The values that I'm modulating are here. This is a parity check. This is data, and basically I multiply then this by this, and I get the number here. And then I sum all the frequencies, and I get a number here and a number here. And then I multiply it by this is the I component, and this is the Q component. Here I didn't put any parity. And then when I join this together, I can sum I and Q, and this is basically the waveform it is transmitted. This is very interesting because this was done in Excel, and the same thing happens when we generate an OFDM signal. There is no analog manipulation of sine waves and so on. Everything is done by using numbers, because these analog sine waves and so on, they are digitized. So each sample has a number associated to it, and what we are doing is processing numbers. That's what makes OFDM very attractive, very efficient. And here, so in this slide, we did the transmitter. In the next slide, what I have done here is a decoder. So same thing again, but now I multiply my combined signal, I plus Q. I multiply by my first subcarrier, my second, third carrier, fourth, and so on. And what I get is that in the end, I get here, as you can see, I get here a number that is plus or minus, but when I go here that I didn't use the subcarrier, what do I get? I get 0. So basically it was able to decode through the dot product, through the orthogonality property, what was the signal I sent. You can see that 12 corresponds to 1 and minus 12 corresponds to minus 1. So basically this is the principle of FDM. I suggest that you do the same thing. You can play with it. It's very easy to implement, and if you follow this spreadsheet here, you will be able to reproduce and create your own OFDM system in Excel. Next topic is how to consider interference, and that's very, very important, because it's not easy to consider interference properly in a network. One thing is to measure interference, but how to add interference, how to consider interference on a global level is very, very difficult. So one thing that I think it was webinar 3 that we covered this, and the way what we did is that we said, well, we need to consider interference as a statistical distribution. And basically what we do here is that we go and we analyze basically for a certain amount of SNR, what percentage of time or traffic we are below it or above it. So, and this will give us what we call availability or outage. And the quality of availability is that we can add availability statistically. We cannot add SNR statistically. And we can also weight availability by traffic, by time, and so on. So this is very, very important. So then what we see next is that we use this measurement of availability. So it's an availability of a certain quality that will result in the customer experience that we covered in the third webinar, basically, where we say, okay, what is the KPIs, what is the customer experience expected? It's greatly dependent of the availability of the SNR. And this implies that we have to do extremely complex and extensive calculations. We take a traffic bin here. So this is, you know, one resolution pixel in our analysis. And in this pixel, we will see that we have sometimes, you know, 40, 50 signals that we can detect. Signal levels with different, coming from different places. Of course, there is the strongest signal level, our best server, and then we have servers, other signal levels that can provide service there. Then we have interference, basically, and then we have signals that are at noise level or below noise level. So what we have to consider is that for two transmitters, S1 and S2, we can calculate for this pixel what is the availability between them. And those availabilities are then statistically added, creating what we call an interference matrix. So basically we have a signal. This signal has a distribution. We have the interferers, and this each one of the interferers have its own distribution. So in the end we have the signal, we have the interference, and then we can say, well, I need a certain signal-to-noise ratio. So what is the my outage? And this is my outage of the signal. Or what is my availability? This is my availability of the signal. Things that are very important to notice is that interference is time-dependent. Interference depends on the location of the interferer user many times. So let's suppose here I have a signal being sent to this UE. This other tower that is using the same resources will be sending an interference signal. Now this interference signal depends on the location of the user. So suddenly now it is, if the user is here, is one thing. If the user is very close, is another thing. Mainly in LTE that you have adaptive, you are changing the modulation scheme, you may be changing power, so the interference varies over time based on the traffic distribution on the interfering cell. So what we had to do is we had to statistically analyze all the possible positions and give a statistical weight and make a distribution of this interferer against this signal. So we come to this scenario here in the bottom. So this is very, very, very important. It's quite intensive in terms of calculations, but it has to be done, and it's the only way to really measure statistically the impact of interference and consequently the customer experience. So to do customer experience based on one single value of SNR is the same thing as doing nothing. And this was downlink. If we look at now at the uplink, you will see that it's even harder because now the interference comes from the user and the user moves. So one time it will come from here, the next time it will come from here, the next time it will come from here. In LTE it can come from several places at the same time. Okay, so all of this has to be considered and analyzed, and this results then in what we call a series of interference matrices. Those interference matrices, they give the relationship, the availability between every single transmitter pair in the network. And this can be depicted as is depicted here graphically, showing the availability of different transmitters. And you can see that some transmitters that are far, they have a stronger interference and transmitters that are close, and so on. So this is the only way to really visualize the network in terms of interference, not just in terms of neighborhood as the majority of the tools do and people do. We also consider physical neighborhood, geographical neighborhood, but the most important thing is the neighborhood based on interference. So having this said, we can go to the second part, that is the network planning. And basically we will talk here about interference again. Actually, no, we already talked about interference. Sorry, this is wrong. We'll speak about BTS and cell ID, link budget, channel assignment, neighborhood, and tracking area. So the first item that we will discuss, and now we are really going into planning and dimensioning. So the first step is it's a planning. We need to establish BTS and cell IDs. Well, first thing that I would like to tell you, what is the difference between BTS, ENB, and cell? And there is a little bit of confusion in the literature, in the 3GPP specifications, and so on. Basically, what 3GPP calls as an ENB is a BTS. It's and the BTS can be one cell or many cells. Okay. Now, a cell is what should be properly called an E-UTRAN cell. Okay, and what creates the confusion is that the 3GPP considers that all the processing will not be done at cell level, but at the BTS level, at the ENB level. So what they say many times when they're referring to processing to be done by a cell, they say, oh, the ENB does this processing. Well, it all depends how the vendor implements. The vendor can implement one processing board per cell or one processing board by BTS, and then have 3 different or 4 or 5 different instances running inside this processor. So, and that creates a little bit of confusion. So just for us to understand, ENB represent base stations, which can have multiple cells. Okay. And the issue that sometimes the standard speaks about ENB doing a certain processing and so on, yes, it can be done at the ENB level, but it applies to a specific cell. So cells are different entities. And cells are identified, some people call cells sectors, but you will see that for us, sectors have, in a multi-technology environment, sectors have a much more broader application than just a cell, because it can have multi-technology cells in it, and basically for us, sector is just an orientation. So we have cells here, and cells have a cell global identifier, identifier that is used by the whole world. Okay, so that's basically it. And then, of course, you are familiar with the mobile country code, with mobile network code. This is specified internationally. This is specified regionally by the country, and uniquely identifies the operator. So with those 2 numbers, you know who is the operator. And this is called Public Land Mobile Network, MCC plus and MNC. And then you have the cell identifier. The cell identifier, you have 2 types, the short ENB and the long ENB. Basically, it's the same thing. And here in the graph, I think it's easier to explain. You have the MCC and MNC. So you already here identify the operator. Now we have to identify the cell. The cell is identified by 28 bits. So you can have up to 268 million cells. I think it's enough. But you know, you take a national operator, it will not have as many. But in reality, this number can be broken in 2 parts. one that is the BTS identifier, the eNB identifier, and one that is the cell identifier per eNB. And basically what you have here is that the eNB identifier has 20 bits, and that identifies about 1 million BTSs. This is wrong here. This should be BTSs. And inside the BTS, you can identify up to 256 cells. You say, why so many? Well, probably you have basically 3 or 6 cells that are the macro cells. Then you will have the microcells, the picocells, the nanocells, and so on. So you need to identify each one of them, and each one of them has to have a global, worldwide identifier, and that's what we are talking here. So there is not much planning to be done, but you have to assign those numbers, because those numbers will be used by the network. Next topic is cell link budget. I will not go very in depth here, because this is probably, for sure, it's understood already by everybody. I will just try to rephrase and show the link budget maybe in a different view. What I found very interesting is that when I explain link budget in this way in a conference, people that were not engineers, they said, wow, for the first time I understood it, and mainly the CFOs, they said, oh, this is like doing accounting. So, you know, I have my gains, my losses, and in the end I have my end result, my profit. And it is exactly the same. Here you can see in blue, you have the signal that arrives to the receiver, and here you have the noise and the interference that also arrives to the receiver, and in the end you have your service margin that will give you the probability of your service being successful or not, and basically express the customer experience here. So that's basically it about the link budget. You're very familiar with it, I'm quite sure, so I will not go much more in depth, but I would like to show, I think, show this interpretation of the link budget. Next item is channel and resource assignment. This is something that I probably get the majority of the questions from the network owners about this, but when we go to the engineers are very shy and try to ignore this step. So let's think a little bit about it. Christina was very fortunate in illustrating this channel and resource assignment strategy. Well, this is like a game of chess. So to select a strategy to assign resources is not an easy task, and can allow you to get a success, or can get you to a checkmate and lose the game. So that's something that you have to spend time on it and effort, and is not something that is done by one person. It requires a group. So I think this depiction here says more than 1,000 words. Even here inside, you know, we are very reluctant sometimes to send one person to help one operator, because what we say is that, look, this person knows so much. Nobody really knows everything. So what we always try to do is to put a lot of people together and mainly discuss the strategy. Later on, when we go, you know, to do the calculations, one person can do it. But the strategy, the actual, this top-level decisions, we need the inputs from different areas, from different experts, and so on. So this is really becoming very, very important. So let's speak a little bit about spectrum and resource assignment strategy. First thing, you know, the question that I get, should I use channels of 5 or 10 or 20 megahertz? Oh, should I have 3 or 6 sectors? Oh, should I, you know, use FDD or TDD and so on and so on. And people ask, as I had the solution. Well, there isn't a single solution. I always say it depends. It depends on your network. It depends on many characteristics of your users, of your geography, and so on and so on. So there isn't really a single best solution, a silver bullet. Doesn't exist. Each case you have to analyze. And even this analysis is not easy to do. So you have to have, first to start, you need to have a deep knowledge of technology. And I see many times a lot of reluctancy, mainly from the C-level, in trying to understand the technology. They think that the technology is above their capabilities. They will never understand it. That's not true. And I had now a seminar I gave to 20 C-level executives, and they were able to follow it and understand the limitations, but it took a while for them to open their minds and listen. So it's very important that the top level of a company understands those issues, because otherwise, the engineers will find the bottlenecks, but this will never flow and things will never change. So it's very important that all levels in the company, including CFOs, including marketing people, they have to have a certain knowledge of the technology. Then an understanding of equipment functionality and parameters. This is more at the engineering level. More than anything else, user traffic characteristic and tonnage. In voice, all of us, independent of the country, we speak the same way. We speak at the same data rate. But when we're going to data, things are totally different. We are having, many different characteristics, data rates, quality requirements, and so on. So if we don't specify all those traffic users and their tonnage, we cannot design a network. And it doesn't matter the number of measurements that we do, live measurements, switch measurements, we will never fix the network. We will be also always running after our own tail. So it's very important, and that's mainly for marketing guys. But the C-level has to understand, and the engineers have to understand it deeply. So proper market modeling, proper equipment modeling, proper cell modeling. I always tell to my customers that modeling the network probably will require between 60 to 70% of an effort of any design. Wrong modeling results in rubbish. Okay, so bad inputs, bad outputs. There is no way. So it's very important to start modeling properly your network. An example, nobody will build a building that is, 100 stories high without doing proper modeling of the terrain, proper designs, and so on. But people are deploying wireless networks with 100 sites without even analyzing what will happen. Oh, let's just collocate with the GSM sites and then we see what happens. Well, you are basically spending a certain capex that you will spend again and again, and your OPEX will bloom, and probably your operation will be jeopardized. So, in resource strategy, you have to think about what reuse factors will be used, what are the limits of each cell considering all the bottlenecks, and how resources should be distributed. That's what you need to define when you do the resource assignment strategies and spectrum usage. First thing that we like to do is do scenarios testing. So what we do, we model the network and then we simplify it and we try different scenarios. So let's try what will happen if this network, if we use 20 megahertz, 10 megahertz, 5, if we use TDD. Well, we explore the different possibilities. Sometimes we don't need to explore all of them because when we do one or two, we already know the trend. So, okay, this is better in this situation. Then what we do is we select, after selecting the channel size, what is better, Omni, 3-sector, 6 sectors, are we going to use no reuse, or are we going to use reuse, and so on. And you will see that sometimes you get very surprising conclusions that are totally unexpected. So in some cases we found that 3 sectors is the best solution. In other cases we found that 6 sectors was the best solution. In some cases reuse of 1. In other cases reuse of 3. So each situation is slightly different, and it will save you a lot of capex and mainly a lot of opex if you do it properly. So, and then after we do this decision, another question always, what is better, 700 low frequencies or 2.5 gigahertz, and so on and so on? Well, there isn't better. It depends on the application, depends on the size of your cells, and in the end it probably will be the same. So, but you have to model it, and one more way of modeling is experimenting with multiple scenarios, because sometimes the outcome is not what you expect that it will be. So let's speak a little bit about spectrum usage strategy. In spectrum usage strategy, of course, we can do many times, we have the option of doing different channel bandwidths. So which channel bandwidth we should use, and so on and so on. So we need to understand a little bit about how the cells will be constructed. We also need to consider if there is what are the RF propagation characteristics. And that's something that sometimes is very difficult for us to make people understand, that different environments have different propagation characteristics. And of course you can take propagation parameters from another area, but you will always get better result if you characterize each one of your areas and you specify the propagation characteristics for it. Then you need to look also for out-of-band attenuation, external interference. One of the things that has been found, and we have been finding, is that interference from wireless phones. So we found that one of our, well, not one, but several of our operators were being interfered by wireless phones imported from the US, and that were in the band and generating interference. And this was an interference that would appear and then disappear, appear and disappear, appear and disappear. Another one is fluorescent lights. Fluorescent lights of certain brands and certain types, they interfere at 700 megahertz. Here Verizon, suppose, has detected this already, and FCC is making some building owners to change all their fluorescent lights because the light bulbs did not comply with the radiation, interference radiation. So of course the vendor had to accept them back. Another thing is that you need to do the simulations, the analysis for different days of the week and different times of the day. You cannot just do it for one and say, I'm done. No, you have to do it properly, and you have to do it several times. So let's speak a little bit about channel resource planning. Of course, to model the different strategies, you have to know what are the available possibilities. And basically, traditionally, we specify what we call a frequency reuse and partitioning scheme. Although LTE was conceived for a reuse of 1, and we will talk much more about this because you will find this as over and over and over, that everything was designed with the idea of reuse of 1, and this brings a lot of bottlenecks, but also brings a lot of qualities. Basically, in LTE, reuse is replaced by repetition. So what is more efficient? Repeat many times the signal or avoid interference. So, and that's we had to analyze, and I will show you some of our results. But basically, the reuse is defined by traditionally 3 numbers. One is the number of cells in a cluster. The other one is the number of of cells in a BTS, and the other one is the number of frequencies available. And there is another one now with LTE and WiMAX and so on, that is the number of partitions inside a channel available. So now we need to have 4 numbers to represent one configuration. So let's analyze the most common configuration, and the one that is being spoken mostly recently is what people call fractional frequency reuse. What does it mean? Well, I did here an example showing 3 different reuses. In this one, is the first one here is the typical LTE reuse scenario. Every single cell uses every single resource. So basically what happens here is that I divide my power between all the resources in a cell. So the power per resource is low because I have to divide between all of them. But of course I will have a lot of interference, and I will replace the reuse by repetition. So I will repeat my signal, so because I have it repeated several times, I can add those repetitions, and I have a stronger signal that I would have just transmitting it once. And then I can, it's equivalent to reuse, but I replace reuse with a repetition. Here, now I divide my subcarriers in 3 blocks. So cell A, cell B, and cell C. Well, when I divide in 3 blocks, what happens? I can have only 1/3 of the resources in each block, but my power increases. Okay, so I go to 3 times higher power. It's about 4.5 dB gain. Okay, so I have more power, I have less resources. This is not very easy to do in LTE because of the 1.05 megahertz central information that I have to have anyway. That's one of the good and bad decisions that was taken by 3GPP. It's good because it allows you to much faster to detect a channel. It's bad because it creates you this kind of difficulties in terms of reuse, but they planned everything with reuse of 1, so they are in the left situation. Well, soon 3GPP found that reuse of 1 has limitations, and maybe if we do some additional reuse, not just repetition, we can increase our capacity. So a lot of the capacity gains been announced in the industry lately in terms of marketing and so on is what they call fractional frequency reuse or fractional resource reuse. Basically what happens here is that I have a tree, the middle scenario, but in the middle of the cell where the UEs are distant from all the interference, I may be able to use all the resources, 100% of the resources. Not around the cell, not here, but in the middle of the cell. Well, that's great in paper. Yes, I can increase the capacity, but generally my traffic is here. I will have very few situations where I have a traffic distributed like this. Another issue is that how do I figure out that the UE is in this region? Well, UE does measurements, it can tell me, what kind of interference, but those measurements represent an overhead, and many times a very heavy overhead. That is one of the things that we have to consider. So if we go to the bottom graph, what we will see here is the following. Well, we still have the 3 main reuses, but part of the power is still low and is distributed for the middle cells, middle positions in the cell. Okay, So this is called fractional reuse, and it's a go. You know, some vendors are applying some algorithms to figure out where the UEs are. Others are using beamforming to figure it out. But all of this, each one of these techniques has its limitations that you as designers need to understand. Okay, so what I did here, I showed you, I will show you some single carrier scenarios first, and then 3 carrier scenarios. So single carrier scenarios, this is the scenario that uses a reuse of 1311, and this scenario is for which the LTE was conceived for. So this is the scenario where LTE was designed for. So basically, LTE replaces resource reuse by stronger forward error correction codes, basically by repetition of the data and the error correction code and the FAC. Okay, so we will show later that this is very similar to regular reuse, sometimes even more efficient. And this was what was adopted by 3GPP. Unfortunately, you know, when we go to non-uniform traffic distributions, things change a little bit, and the reuse of 1 may become not as efficient as it looks. Okay, so 3GPP then consider, okay, yes, maybe this is not the optimum, but we can use this mixed with something else. And this now is where we use the, we break the resources in 3. You will see later on that our simulations show that for uniform traffic distribution, reuse of 1 and reuse of 3 provide very, very similar results, with reuse of 3 providing faster data throughputs, but the tonnage is very, very similar. It even for regular traffic distribution, it is even better, slightly better for reuse of 1. And then we have the fractional reuse possibility that we already explained. And here you can see that we have the 3 cells, and then we repeat this and repeat this. So the interference between 1A and 1A has a certain distance here. Okay, and same thing for 1C and 1C, and well, it was closest here. So we have at least 1 radius of distance between the interference. So having the adaptive modulation, it's very, very good because it allows you to adjust to the level of interference that you have. So this was a good thing that was done in terms of analyzing and so on. But for sure, reuse of 1 requires some kind of protection to improve the capacity in the end. Then we have the 3 carrier scenarios. A lot of operators that we work with, they said, well, I have more than 1. Should I use 5 megahertz, 10 megahertz? Well, wider the channel you use, more efficient you will be in terms of carrying data, but you will be less efficient in terms of interference. So if you have several carriers, you have to analyze, as I said before, the different scenarios and choose and decide which one. Here, in each cell, we use a different carrier. Okay. So this is a 13331. This now is a reuse of 9. Well, how efficient? Well, of course, reuse of 9 is much more efficient in terms of interference, but I only can carry 1/9 of the resources, and then it becomes a problem. So I can do something like this, that's a fractional mixed reuse with 3 carriers. The only thing is here, in this case, suppose I have, actually this is a 2 carrier scenario where I have 1 carrier in the periphery and 1 carrier, a different carrier in the center, and then I still have partitioning on top of it and so on. So you have really to model, and that's what we need to do. Another thing that is very important is neighborhood. LTE foresees that, well, neighborhood can be done automatically by the cells, using the UE information. And this is partially true. Yes, it helps, but it should start, in our opinion, from a neighborhood defined by the design. Because what happens is that UE can measure something and one neighborhood may not exist when the UE is measuring. Okay, nobody's transmitting there. Or it's transmitting in somewhere else in the band, and the UE cannot measure the neighborhood. And then suddenly, you know, the neighborhood is there available, but it was not measured. And when you need it, what happens? So you need to have a base that is based on the design, and then you work and optimize this base based on the UE measurements. But I don't think one should eliminate the other. I think you need to have both. And here we show, you know, primary first level neighborhood and second level neighborhoods, and you can see that some neighborhoods are very, very far apart. And that's what we call interference neighborhood, not geographic neighborhoods. So in red we depict primary neighbors, and in blue secondary neighbors. And this is done automatically by our tool. Then also handover information is very, very important, and basically we calculate what is the average signal in between two cells and what is the standard distribution, so we can properly establish the handover parameters, handover hysteresis, and so on, or handover levels. Another thing that has to be dimensions is the tracking area. Basically what happens is that there is a cell tracking area code, TACT, that is broadcast in the system information broadcast 1. So the ENB broadcasts this information telling that this cell belongs to this cell tracking area. So what we need to establish here is first that we need to have pools of MMEs. So in a large network you have many MMEs. Those MMEs, they speak between themselves and they form a pool. And this pool will control one or more tracking areas. Okay, basically tracking areas is the areas where the paging will be done. Then you have other pools that can overlap with the previous pool that will have also other tracking areas. And you have pools, MME pools that do not overlap, and they have their unique tracking areas. So basically, the tracking area, the TIE tracking area identity is defined by the MSC, MNC, and the TAC. So because 3GPP allows you to cell to have 6 PLMNs, you can have up to 6 ties per cell. And the UE, that's very important, can register with multiple ties when it is in idle mode, because if it is in the border between two ties, it may register here and it may register here at the same time. So we will get paging messages on both. A little bit about frequency and resource allocation tools. Well, you see the complexity of doing those calculations. So you really need tools that allow you to do those calculations automatically, that allow you to specify, to block channel resources, that use advanced simulation techniques like simulation annealing and so on, and that uses scores to do benchmark tests that are based on availability, not, you know, on random numbers that somebody took from a hat or something like this. So then we need to do code optimization, frequency optimization, and so on. And the tool must be able to allow you to visualize those plans. We find this very useful because a tool can be only as intelligent as the information we feed into it. And if the information never is perfect, so it's always good to check and do a sanity check before deploying the plan. And the visualization of the plan is very, very important. Okay, I think we reached now a break point. Christine, you have questions?
Yes, there's a couple of questions. The first is a question slash a comment. Is just a couple of people asked if you, when you're talking about the parameters, if there's any that are specific for FTD or TDD, if you could highlight that. And then a question which is, what's the difference between cell ID and PCI?
Okay, everything that I'm talking here today, it basically applies to both FDD and TDD. There are small, probably in the random access channel, there are some twists. I will be focusing more on the FDD layout, but the parameters are the same. So it applies to both technologies. About the difference between cell ID and PCI, well, we didn't talk about PCI. Cell ID is basically an address at a global level. So we must be able, at a global level, be able to specify a specific cell within the world. While PCI, we will see later on, it's a cell address, it's a cell code, but it is only valid within a specific network. So it's a much shorter, you will see that, and it's only valid inside a network. So the same PCI can be reused even inside the network. So you can have people with the same PCI, cells with the same PCI within the same network, because there is a limited number of PCIs available. And the only reason to use PCI is to distinguish the cells that have similar configurations. And we will talk a lot about this, and that's what will be our next topic here, downlink, dimensioning, and planning, and that's where we will talk about PCI. And actually, the next slide is physical cell ID, PCI planning. So this was a very timely question.
There's a couple more questions if you have time.
Okay. No, yeah, of course.
Okay, the next one is, why SC-FDMA is used for uplink rather than using standard OFDM, such as in downlink?
Well, to be sincere, in my opinion, the only reason is that LTE had to be different from WiMAX. I think this was a bad decision from 3GPP. The argument was that it will help in terms of PAP, peak to average power rate, and because OFDM tends to build in some places a large peak, and this will requires large power amplifiers and so on. And yes, it does reduce PAP by few dBs, 3-4 dBs, but it creates a distortion of 3-4 dBs. So there was not really a gain there, but there was a loss, and the loss is SC-FDMA requires contiguous subcarriers, and you lose diversity. So one, I think, of the drawbacks of LTE when compared to WiMAX is the fact that they don't have the subcarrier permutation. And with this, they lost a lot of diversity. And lately, 3GPP is trying to compensate this. So in the uplink already, it allows the transmission of one block or more than one block of SC-FDMA. So it's nulling and at the same time transmitting the control channels. So it's basically nulling the advantage of SC-FDMA. But this was a decision taken in the beginning, and now we have to live with it. Next.
I think that's it for now. There's a couple others you can follow up by email later.
Yeah, we have a lot of things to cover today, so let's follow. Yeah, let's continue. So let's speak about PCI planning. Well, PCI is a very, very important parameter to be planned in a LTE network because it affects many other parameters. So we will see that it affects PSS, and PSS requires a reuse of 3 between cells. So we should avoid that the neighbor cells use the same PSS. And there are 3 codes, so we need to plan PCI with a reuse of 3, and the PSS chooses its code based on PCI. SSS also is PSS is primary synchronization signal, SSS is secondary synchronization signals. Well, but I have 168 SSSs. Well, I still need to plan them. And basically what we do here, we use the number of 150 to do this plan, because we leave 18 for picocells. And we plan the macro cells with 150. You can plan also with a lesser number. If you have more picocells, you can plan with 90. But I think 150 is a good compromise, at least for today. And the other one is the cell reference signal. The cell reference signal, you should not use the same reference signals in neighboring cells. And well, not the same reference signal. You should not use the same position of the reference signal in neighboring cells. And there are 6 possible positions of reference signals, so you have to plan PCI based on reuse of 6. Also on the uplink, a lot of the access is done by orthogonal codes. And those orthogonal codes, there are 30 groups of them, so we have to do, and the choice of those 30 groups is also based on the PCI. So now we have to have a reuse of 30. So in reality, when we are going to plan PCI, we have to plan it with a reuse of 3, 6, 30, and 150. And that's why it is very, very important. And this planning cannot be based only on geographical neighborhood. It should be based on interference neighborhood and the geographical neighborhood. So when you calculate the neighbors to do this planning, you have to consider both. Okay, and it's not good enough to use, neighborhood defined or found by the switch algorithms and so on. Because what we found is that this is very, very deficient. And in many cases, people have systems, networks that are starting, and they just use the neighborhood that is there. But there is not enough traffic to create this neighborhood. So you really need to do this with a planning tool. So physical cell identity, or PCI, is different from cell ID, as we already told. There are 504 PCI codes in an LTE network, and those PCI codes are organized in 168 groups of 3. Okay, well, you can ignore this, but that's basically is one initial division just to help you to organize so the 3 will be the ones that will define the PSS, and then you have 168 other groups and so on. That we really, in the end, we use 150 groups. Because PCI, why it's so important? Because it's used to index many different network parameters like PSS, SSS, CRS, and GBS. Okay, so that's why the PCI planning is so important. Well, let's go to the primary synchronization signal. Let's understand a little bit about it. I will not go in great depth here, but just a small recapitulation about PSS. Well, PSS uses a Zadoff-Chu root sequence based on, this is wrong, not based on cell ID, but based on PCI and mode 3. So if you divide, PCI by 3, you have the remaining, and this remaining is the one that gives the which code, Zadoff-Chu root code, will be used. It uses QPSK modulation and send in last slot 0 and 10 of every frame. It uses 72 subcarriers, of which 62 symbols and blanks the remaining 10 symbols. So 5 symbols on each side are blanked, and the PSS is shown here. Is this signal in the middle here. And well, this is just a curiosity. Why it is, if it is the primary, why it comes after the secondary? Well, because after you find the primary, the next one to appear will be the secondary. So you will not have enough time if the secondary appears immediately after. So it's just a small detail. Okay, then we have the secondary synchronization signal. Well, this is the secondary synchronization signals, and you have in reality 168 pseudo-random code sequences, and those sequences on the first appearance on the frame are different from the sequences of the second appearance of the frame, and this is what allows you to define the start of the frame. Otherwise, you would not know if this frame starts in the middle or in the beginning. So it's these two different sequences that allow you to figure out where the frame starts. It also uses QPSK modulation, and it's based on an interleaved concatenation of two length 31 binary sequences. And these binary sequences are scrambled by the primary synchronization signal. So it's a quite complex signal to generate, and it also uses the 72 subcarriers with 10 symbols blanked here on the sides. Let's speak about cell reference signals. Well, LTE has many reference signals, and here is a list of them. We will concentrate on the cell-specific reference signal because this signal is the one used to decode the information that was sent. It's like a pilot. You know the content of the signal, so by knowing what was sent, it's easier to adjust the losses and distortion of the RF channel. So I am supposed to receive X, so let's move my gain, my phase until I get X, and then you know that at that subcarrier, at that symbol, at that resource element, how you have to adjust the RF channel, and then for the other one, and then interpolate between the reference signals. The other ones are used with for specific purposes. They are not as frequent, and they are not mandatory. So for now, we will ignore them, but they also will use PCI, and they don't require a special PCI planning beside the one that we are speaking here for the other signals. So the cell-specific reference signal carries one of 168 length pseudo-random code sequences, and it is sent. You need to have the signal per antenna port. So you need really to send it in every single antenna port. But if you send it in all the antenna ports at the same time, they will be mixed together, and you will not be able to decode the signals sent by each port. So what happens is that a reference signal is sent 8 times per resource block pair. In a subframe resource block, you send 8 of them. But the other ones, the other antennas, also have 8. So if you have 8 antennas, you have 32 resource elements carrying those, and they will be shifted. By being shifted, and here I have a depiction of one resource block with 12 subcarriers here, and 7 slots here. So basically I have for port 0, port 1, and then port 2 and port 3. So the 4 antennas are depicted here. And when in all the antennas, when it's time to send a reference signal from another antenna, all the other antennas, they are blanked. They send DRX, discontinuous transmission, DTX, excuse me, that's wrong here. So they don't send anything, they are blank, so you lose those resource elements. So they are overheads. But you also don't want in neighbor cells to send the reference signal in the same position, because then you will have a lot of interference. So in LTE, 3GPP specifies 6 positions for an antenna reference signal. And you see it moves by 1 resource element each time, depending on the PCI. That's why the PCI has to be planned with a reuse of 6, basically to allow that neighboring cells do not have each antenna reference signal in the same position. A little bit about uplink group-based sequences. And I apologize here that you cannot make live questions, but otherwise we will not finish a webinar. This is generally something that we do in our classes, and it takes days. And we interact with the participants, we make questions, we make exercise. So uplink-based group sequence. Well, there are 30 groups, as I already said, of base sequences that are available for PUCCH, DMRS, PUSCH, DMRS, SRS, and PUCCH. So basically, they are all applied in the uplink. But the decision to use one or the other is based on the cell PCI. Okay. So I said 30 groups. So each group, of course, has more than one sequence. So in each group we have one sequence. Well, we will explain this better here. It's hard to phrase it, but it has several sequences of, it has one sequence of length 1, 2, 3, 4, and 5. Then it has 2 sequences for every length above 5 up to 100. And of course it depends on the bandwidth, the final length to be used. So we should avoid to use same groups in neighbor cells. And the reason for this is that inside the group the sequences are orthogonal, but between groups they are not. So that's why the reason that we have to space the groups so they are not neighbors. Groups can be used by the, of course, PCI can be used to define the groups, and we use PCI mod 30 generally to do this distribution. But there are also additional parameters that are used to assign this, and we will discuss this in much more detail when we go to the different each one of these channels. But here I illustrated basically. You see, there are 12 sequences here that for one resource block. For 2 resource blocks, for 3 resource blocks, for 4 resource blocks, and for 5 resource blocks, I have those sequences here. This is a sequence of 12, excuse me, not 12 sequences. There is a sequence of 12. Here's a sequence of 24, here's 36, here's a sequence of 60. Above this we have 2 sequences, sequence A and sequence B for each one, for each number of resource blocks up to 100. Let's speak about PCI planning. Well, remember we need to use a reuse of 3. So now we need to use a reuse of 6. So we need to keep the reuse of 3. So here what I did, we kept the reuse of 3, but we also have a reuse of 6. So now we just can replicate this. Of course, this looks very beautiful in a uniform distribution. In real life, this is much more complex. It's based on interference. The cells are not regular, and you cannot do it by hand. You have to do it. But in order to understand the process, you should start doing it by hand first, and then. So here I have a reuse of 30. So basically, I will do my PCN plan in trees. Then I will take groups of trees and form groups of 6. Then I will take groups of 6 and form groups of 30. Then I will repeat the groups of 30 to form groups of 150, and then I will have groups of 150. So our tool cell designer considers RF interference in geometry to automatically populate the PCIs. It's always good to reserve some PCIs for small cells. Geralmente, I think 18 groups is something that is feasible. Okay, now let's speak a little bit about downlink dimensioning. And there are many parameters that we have to dimension. Cyclic prefix, PFICH, PHICH, PDCCH, CCEs, PDSCH, and RBGs. And we will explain each one of those, and you will see that the understanding of those parameters is as important as dimensioning. A lot of people, well, I will use the default. Yes, you will use therefore you are probably leaving a lot of money on the table because you're not optimizing your network. Okay, so you really need to analyze. The first one looks like the simplest one, but probably is one of the tougher ones, is the cyclic prefix. You know already what the cyclic prefix is. I will not explain it, but basically is where the multipath is mitigated, is the multipath guard band, okay? So if you properly design the duration of the cyclic prefix, we should be free of multipath, and that we should get better throughput and everything on. In this table here, basically, LTE only allows you to choose between two different cyclic prefixes, the normal and the extended. The normal allows for a multipath of 1.4 kilometers and the extended of 5 kilometers. So larger cells than 5 kilometers will not work. 5 kilometers of multipath spread, and don't mix this with radius. So it's not a 5 kilometers radius. What it means is that if we have a cell, okay, and we have the center of the cell and we have a user here, the user can get one signal here and then a reflected multipath here. So the multipath spread is the difference between all the multipaths between this, the direct path or the shortest path, and all the others. So the cell radius may be huge, but the multipath may be still 5 kilometers. So there isn't really a direct relationship. And that's where the issue starts. How do I know what is my multipath? Well, there was really tools to measure it. So we developed Cell Spectrum because we had to do this for our customers and we didn't know how to measure. So it was always a guess based, I believe it's so much. Then we developed this tool. Is a software-defined receiver that allows us to do a lot of spectral analysis and so on. And basically here, what we are showing is all the multipaths that we receive. We are using the PSS power delay profile. And basically here is the main PSS that we detected. And here you can see that we have several large multipaths. Look at this last one. Okay, and then what we do, we measure this time here up to a certain level and say, well, this should be the size of our normal prefix. What is happening today is that operators generally, they want more capacity. Let's use normal prefix. Well, the cyclic prefix can be dimensioned per cell. So it doesn't need to be the same in all cells. And we have done measurements with commercial operators, mainly here in our area, and we have found that in many cells they have multiparts that are larger than the normal cyclic prefix that they are using. So it's very, very important to be able to measure. Here is our drive tests, the measurement results, and this is a two-dimensional measurement. And those measurements then we can analyze for the whole area of the cell, and then we get different, of course, values. You see, this one is for this point, this one is for this point. You can see how it varies with where you are in the cell. And based on this, then we select what is the cyclic prefix that we can use. Another channel that we have to dimension is the physical control format indicator channel. Well, this is a channel that is relatively complex, but the only information it gives me is how many control symbols I will have in a TTI. So basically, the channel format indicator signals if I will use 1, 2, or 3 control signals in a frame. And basically it's spread by a length 31 pseudo-random code sequence, and it's sent over 4 resource element groups. This is a very important unit in LTE. 4 resource elements is called a reg or quadruplet. Reg RE or quadruplet, and basically this signal requires 4 of those quadruplets, so it has 16 resource elements allocated to it. Because it uses QPSK, it can send 32 bits, and wow, what a coincidence, 32 pseudo-random code sequence. And here we show the reference signals, we show the blank reference signals that are the time that the other antennas are transmitting, and then we show in colors the 4 quadruplets. Okay, the PCFICH quadruplets. And basically those quadruplets that here are shown in red, you can see that they are not contiguous. They have to give room for the reference signals and also for the blank signals. But basically by reading this, we will know if what you have here depicted in light red, how many symbols we will use for control information. And control information basically is mapping or where the data will be in the remaining of the TTI. So the other channel is the physical hybrid. So there is nothing really to do with PFICH, but to specify how many, what number we want it to show, 1, 2, or 3. Okay. If we are using a 1.4 megahertz, 1 corresponds to 2, 2 to 3, and 3 to 4 symbols. So, but that's an exception. Not many people use 1.4, so let's ignore it for now. But basically, the only thing that the PCFICH channel does, and that's what you need to dimension. Do you want 1, 2, or 3? How do you dimension this? Well, we'll see this a little bit later. It depends on the number of packets that you will be sending, because each packet has a map. Now, the packet that you are sending is not the packet that you are receiving, and we will discuss this in much more details as we go forward. So let's speak about physical hybrid IRQ indication channel. Well, we will talk about this. We will talk about scaling factor, and we will talk also about location. So this is also another channel that doesn't have much information. One thing that we will detect when we analyze the MIB is basically what is the scaling factor. The scaling factor defines how much information of ACNAC we need to send. Basically, the PHCH channel is made of 3 regs. Remember, a reg is 4 resource element. Well, for one channel, you need 3 regs. So you need 12 resource elements, a little bit less than the other one. And the only thing that you send here is ACNAC. Okay, in this, so it's a highly repetitive, like the other one. It's a high repetition because those places you have 100% interference with all the cells. So there is nothing really you can do, but the only way to avoid interference is by repetition. Now, you can have more than one PHCH group depending on the scaling factor and depending on your bandwidth. So if you specify a scaling factor of 1/6, or let's start with 1, you specify 1, this is the number of quadruplets, 3 times quadruplets that you will have. 1, 2, 4, up to 13. And then you can go down or you can go up. It depends on the number of packets that you will need to map in each TTI. Each group is shared by 8 UEs using orthogonal sequences. So when I say here that I have 13 groups in 20 megahertz, it means that I can, well, let's say 10 groups in 15 megahertz, or 7 groups in 10 megahertz. I can support 56 ACNACs from 56 UEs per TTI. Okay, so it depends very much on the size of the packet that you will be manipulating. That's why we said that the user definition, user traffic definition in detail is so important, because we will use this definition to calculate how many of those channels we need to use, and more channels we use, less resources we have. The position of those channels is PCI dependent. So depending on the PCI, and the idea here again is to avoid that neighboring cells have the same channel in the same place. You still will have interference between different channels. You have traffic channels, you have control information, but you try to avoid that the same code that you are using here, the same spreading code, is repeated in neighboring cells. So that's why here basically what we show is with different, suppose for PCI 0, that's how it will look, but for PCI 1 you can see that it is shifted by 1. The yellow ones are the PCFICH, and the other ones are the PHICH from 1, 2, 3, 4, 5 channels. Okay. Well, so in the control area, that are the first 1, 2, or 3 symbols of the TTI, we already have the PFICH and we already have the PHICH. What is left in this control area will be used by the physical downlink control channel, abbreviated PDCCH. And in each TTI, we have to calculate how many control channels can we place. And you will see that this is not a trivial calculation, because the size of the control channel is adaptive. We will also introduce here the concept of the downlink control information and the CCE, the control channel element. Basically, the way those elements are related to each other is that the ENB and the UE, when the UE registers with an ENB, it agrees with the ENB on what we call a transmission mode. So basically the capabilities of the UE and the capabilities of the eNB are compared, the type and the transmission mode is selected. Now in reality the transmission mode supports more than one transmission mode, because again the transmission mode is adaptive, because the situation can change, and it's adaptive not just with the RF channel, but it's adaptive with the type of information being sent. So once the transmission mode is established, and this is established when the UE registers, then the downlink control information format can be defined. And this format basically is the format of the mapping information. So once we know what is the transmission mode, we say, well, we are using this format then to send. And this is very important because this is not informed. The eNB, the only thing that is informed between eNB and the UE is the transmission mode during registration. After this, the UE and eNB have to choose the same DCI format, and they will be used the 3GPP specifications, the LTE specifications, so they choose the same DCI format. Once the DCI format, this format will be carried by a PDCCH channel. Now, the PDCCH channel, that the physical downlink control channel, carries then the information of the DCI for the UE to read. Now, this UE can be anywhere in the cell. Of course, after the first connection, it's possible to establish how good is the signal that the UE is being receiving, but the PDCCH channel in LTE specification does not have any protection. It's 100% interference from the neighbor cells. So what 3GPP did, they allowed this channel to use very high repetition rate. You will see that repetition rate can reach 25 in few cases, but it can be also 1. So the way to protect this channel, this information, is to have a special format coding rate for it. Once this is defined, we can define how much channel control elements can we put in the PDCCH in the control area. Because a control channel element, it's basically one map. Oh, excuse me, no. It's a set of 9 quadruplets. It's a fixed set of 9 quadruplets. So this fixed set of 9 quadruplets is the smallest amount that I can use to send DCI. So the smallest amount is 9 quadruplets, that is 36 resource elements. And this had to be created for one reason. So we have predefined locations in the control channel. But remember that those predefined locations depend on how many, what resource elements were removed for the reference signal, what resource elements were removed for the PCFICH, for the PHICH, which locations depend on the PCI. So the eNB and the UE, they have to do the same calculations to figure out where the CCEs are, and then to figure out how many CCEs we can fit. Well, because also, and then those CCEs, the number of CCEs used will depend on the DCI selected and on the PDCCH format coding rate. So we can send a DCI in 1 CCE, in 2 CCEs, in 3 CCEs, in 4 CCEs, and so on and so on. Of course, if one DCI uses more CCEs, less capacity of mapping I will have. So all of this has to be analyzed and considered So let's go a little bit now. I think I explained a lot about for you already, so we can go faster in the next slides. Basically, what we have here now is, excuse me. Okay, so what we are going to do, what we want to do in this this channel has to transfer DCI information, doubling control information. That basically gives me data mapping allocations. One thing that I didn't say before, I forgot. The reason that we need to have the CCEs is because I will ask you a question. Who tells you where the mapping information is? Well, the UE doesn't know. The only thing the UE knows is that there are CCEs and it can calculate where the CCEs are. Well, to find out where the mapping information is, the CCE has to do the UE has to do blind decoding on every CCE position to figure out where the mapping information is. And then by finding the mapping information, the DCI, it can find out where the data is. Okay, so basically here we have a TTI, and in this yellow area we have what we call the control area. So this control area carries what? It carries reference signals based on PCI, the location. It carries blank signals for the other antennas based on location based on PCI. It carries the PHICH quadruplets, 4 quadruplets, whose location is based on PCI. It carries the PHICH 3 times quadruplets times number of groups. That is also location based on PCI. Whatever is left will carry the PDCCH channel. And the PCCH channel will use CCEs. Those CCEs are groups of 9 quadruplets, 36 resource elements. And the PDCCH then can use different numbers of CCEs. And this is defined here by the PDCCH format that the ENB selects to send the information. So format 0 will have 1 CCE, 9 quadruplets, or 72 bits. Why 72? 9 times 4, 36. It's QPSK, 2 bits per symbol, 72 bits. Or it will have PDCH format 3, that it will have now 72 quadruplets, 8 CCEs, and it will have 576 bits. But remember, format 0 and format 3, they are taking the same information, that is 1 DCI. The rest is spreading, is repetition, all the other bits. And 1 DCI has, you will see, in average between 35 and 50 bits only. So everything else is spreading depending on the quality of the RF channel and on the interference that comes, but mainly interference, because there is no protection in LTE for this channel. So it is, all the neighbors will interfere there. So the only way really to pass the information is to improve. And you will see that this kind of spreading is very, very large. So suppose you have a 30-bit DCI and you spread it to 576 bits, you can see what kind of repetition are we using here. Okay. So we have several CCEs. If we have a very large bandwidth, we have many CCEs. What happens is that the UE, it doesn't know really what of this format was chosen, which format was chosen, 0, 1, 2, or 3. So it has to go at each CCE and then go there and test it. Go to the next CCE and test it. and test it and test. So it's what we call blind decoding. To simplify this, to minimize this processing that eats a lot of UE battery, what was decided is that 3GPP said, okay, let's divide the CCEs in two search spaces. One we call a common search space and another a UE specific search space. Well, the common search space will have some CCEs that will be used mainly for broadcasting, for assessing UEs for the first time, and so on and so on. And then when a UE is expecting something that is not a broadcast, we'll make a second group that is smaller that will have the UE specific messages, and so on and so on. So the 3GPP specifies several aggregation levels and so on that allows you to choose the best, to divide the number of CCEs in search spaces to minimize the blind decoding effort. So basically we have a quadruplet, then we have a resource group element, we have the control channel element, and we have finally the search space. That's how the PDCCH constitution is done. Okay, we will use all of those concepts as we evolve. So basically I divided this in concept, we understand the concept, and then we have to have several concepts together to be able to do the dimensioning. That's why I have to do blocks that they look loose, but they are not loose really, they are all interconnected. Another one that we want to discuss topic is radio network temporary identifier. Remember the cell ID? Cell ID is huge, right? So each time I want to refer to the to a UE, if I want to use a cell ID, I will spend a lot of bits, and you will see that in LTE every single bit is crucial because I have to repeat the bit many times to make it work. So I even, I have an expression here saying that LTE is a bit scrubbing technology. So you will see that they go to a humongous extents to save one bit and increasing complexity many-fold. So what was decided then is that the cell will use nicknames. And the same UE may have different nicknames depending on the process, on the stage, and sometimes even simultaneous nicknames. And those nicknames are called radio network temporary identifiers, because when the UE changes from one cell to the other, it gets another nickname. This is just to show you the complexity of identification inside an LTE network. We have here the different elements, the UE, the ENB, the S gateway, the P gateway, the MME, the PCRF, the MSS, and the SPR, and these are neighbor MME, and then the PDN network and so on. Each one of them has different identities, and the identities to use between the transactions between those elements may be also different. So here I made a list of possible identities, but of course we don't need to know all of them, we need that they exist. So if somebody speaks to you about GUTI or about MMA or TMZ, you need to know what it is that it exists. But which are the identities that we are concerned when we are doing planning? Those are the identities that we are concerned. Some identities, they are what we call broadcast identities, and they apply to all the UEs. So all the information about the system information is coded by identity code SI-RNTI. And you will see that LTE doesn't use an address, a formal address. So it doesn't really write, send this message is for UE John. Instead of this, it takes error detection code, CRC, and it scrambles with the identity. So what the UE has to do, it goes in the CCEs, in each CCE, it goes where the CRC will be, and it unscrambles the CRC with its own identity or its broadcast identity, and then it checks the CRC. If CRC matches, then the message was for John. Okay? So, but it has to do this with more than one identity. First, it has to do it with the SI identity. Well, is this a broadcast message? Then it has to do it with a paging identity. Is there a paging for John, for me? Because paging is sent with everybody, it will not have the name of John. It will have a name of a paging identity. And then this is for multicast also, if the multicast is implemented in the system. Now, depending on the stage that the UE is, there are other identities that it has to consider. If the identity is accessing the system, it should, if the UE is accessing the system, it should use the random access RNTI. It has a temporary cell identity that is the UE identity in the cell. It has a temporary one, and then it has a definitive one after it has a successful access. It has a semi-permanent scheduling identity, and it has a transmit power control identities for UCCH and USCH. So you can see that a single UE has several identities that vary on the context, by the context, and it has to blind decode every CCE position inside the relevant saved space with each one of those identities. And this is one of the reasons that batteries are consumed a lot. So, and the reason for this is what I call the principle of bit scrubbing. LTE had to simplify the number of bits, reduce the number of bits to the maximum because of the repetition, and the repetition eats throughput. Here I have in this table the addresses to that are used. Why I want to know how many addresses? Well, it's very important to know, to understand. So SI, system information, has only one address. Everybody uses the same address. Paging has only one address, and multicasting has only one address. So those three, basically, all the UEs have to check for them. If they are in a random access, there are 60 values, and the UE, you will see, it will pick one of these values and be checking if its access was successful. And then for the others one, there are 65,463. But the same UE can have this, 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 and this. So it's 1/4 of those really, or 1/5 of those that are available. So I can still have about 12,000 UEs being active, not active, but being present in my cell with addresses that they didn't release. So let's speak about the common channel element. Let's visualize the common channel element. So what I did here, I basically have, this is 75, this is a 20 megahertz channel, I believe. No, 49, 50, 75. Yeah. Okay, this is basically one quadruplet. Now this is a 10 megahertz channel. So I have one quadruplet, two quadruplets. I have 75 quadruplets that I am representing here. It didn't fit in one line. It should be in one line, but then you cannot see the numbers. It becomes ridiculous. So here basically I placed the PFICH and the PHICH quadruplets. It goes all the way up to here, and then I start numbering the CCEs. So CCE 0 is 1, 2, 3, 4, 5, 6, 7, 8, it should be 9. Oh, 4, 4, 8, 9. So this is CCE 0. You can see that it's not contiguous. Then you have CCE 1. Remember that this is one after the other. Then I have CCE 1 until here, CCE 2, and so on. So in this case, I have 17 CCEs that are a large one, and the last one didn't fit, so I don't have this one because it has only 8. So I have 17, 18 CCEs in reality, start from 0. So what the UE has to do is go to each one of them, look at the CRC that uses here 16 bits, and check the CRC, decode it, descrambled it with its temporary IDs, and then check if the CRC matches. If it doesn't match, it goes to the next. But the match can be against 1 CCE, 2 CCEs, 3 CCEs, and 4 CCEs. So it's really an amazing amount of calculations that is done by the UE. So here I made a summary of, for different bandwidths, how many resource blocks you have, and then how many CCEs you have, how many regs, and how many CCEs do you have available per symbol. So here I give an example. Using PCFICH of 1, PHICH of 2, I can have those CCEs here. Now if I use a PFCH of 3, so now I have 3 symbols, and I have a PHCH of 1/6, the smallest PHICH, I can have this number of CCEs. So you can see that the number of CCEs varies a lot depending on the bandwidth, and some configurations are not even possible because, of course, I cannot have 0 CCEs, otherwise I cannot send mapping information. So for a small bandwidth, some configurations are not allowed. Very well, we spoke a lot about the mapping information. Let's speak a little bit about the PDSCH. That is where is the channel that carries the traffic and signaling information. And we will speak about another concept that is resource block group that is essential to this. Well, this channel PDSCH, as you can see, it carries a lot of information of different channels, different logical channels. So it carries user traffic, but it also carries signaling message like paging, like control broadcast channels, control channels, and so on. So the traffic channel is here. It's one of the channels. So there is a lot of signaling overhead on those remaining symbols in the TTI, and that has to be also measured and considered. So it basically sends the SIBs, the broadcast system information. SIB is a very important thing that you need to remember. Broadcast paging messages, downlink radio resource control signaling messages, and then it sends the DCIs, the DCIs sending the PDCCH are the ones that will tell where those resources are. So every single of these packets has to be mapped. So when we send a paging message, we need to tell where this message starts and how big it is. But in 3GPP, nothing is so simple because of this bit scrubbing principle, you will see that instead of declaring where the message is and how big it is, it uses all kinds of tricks to minimize the number of bits, and we will discuss this. System and paging messages, they always use QPSK. So everything broadcast is QPSK. The rest use adaptive modulation, QPSK 16 QAM or 64 QAM. Then we have the paging control channels. Basically, I will not go in details here. You have the slide. And we have the downlink shared channel that basically has, here we need to look to understand it. Because the data is in what we call a transport block, and we will speak much more about transport block going forward. So this transport block gets a 24-bit CRC. Okay, it can be segmented because if it is more than 6,120 bit large, it has to be broken because of the turbo code, and each block gets another 24-bit CRC. Sometimes we need to put some filler bits, and then we apply a turbo code FAC mother code of 1/3. So data is 1, error correction is 2. So it's 1 of data in a total of 3. Then we do interleaving and we do scrambling with the cell ID, and then we will do rate matching to link conditions. So what the rate matching will do, it can puncture or it can repeat and then puncture. So in the end, what we have is an adjusted code to the requirements of the RF channel. Well, the next topic is very, very important, is how resource allocation is done in the PDSCH channel. Basically how signaling and user data is allocated. Unfortunately, it's extremely complex. So I will try to explain it here the best way possible. But what we need to understand is the concept of a transport block. And we will speak much more about transport block. But basically a transport block, in principle, we can make an analogy of a packet, a wireless packet that is not the IP packet that was sent. It may be even coincide with an IP packet, but it may not. And most probably it will, well, in some cases it will, in some cases it will not. This transport block, because of turbo coding, it has to be broken in code blocks, and then it has to be modulated with a certain coding rate that the ENB estimates. When it's modulated, it goes, it uses a modulation encoding scheme, and it, based on the modulation encoding scheme, it is mapped to a transport block size index table. Then this table will tell us how many block, this is wrong, this should be R. Resource block pairs should we use. Okay, once we define the number of resource block pairs, then we can define, automatically we are defining the PDSCH format, and then we can define how many transport block groups we should allocate. We can and then we define the code words, and we can then do the mapping specified by the DCI to the different resource elements. So it's a very extensive process, and we will break it here in blocks. Before we start, we need to understand what we mean by a resource block group. You know that a resource block is 12 subcarriers by 6 or 7 symbols. Well, this is not the smallest the smallest block that can be transmitted. Depending on the number of the bandwidth, this is the number of resource groups. What 3GPP does, it defines a resource block group size. So it says you cannot, if you have a 5 megahertz bandwidth, the minimum transmit size that you can have, you should use is 2 resource block pairs. What I mean pairs is the 2 slots, the resource blocks in 2 slots. They don't need to be one under the other. For diversity reasons, you will see that sometimes some formats split them. There is a lot of formats. It's something also very complex. So this is the size of resource block groups, and this is the number of resource block groups in the bandwidth. Okay. One way of mapping those resource block groups, and why did 3GPP create the concept of resource block groups? Because it has to map them. One way of mapping is do a bitmap. So say resource block group 1 is used, 2 is not used, and so on and so on. So here you need to have 25 bits instead of 100. And according to the bit scubbing principle used by 3GPP, that was one way of saving bits, is creating larger groups. But of course this also minimizes efficiency and throughput on the transport channel, but it helps the control channel, the control area. Resource block groups are numbered, and also you number them by subframe from right to left. Some resource block groups are smaller, the end ones, and you can number them in per frame basis. Okay, so the 00 up to 129, 130 resource block groups. But remember that inside here you have reference signals. You have, in some of them, you will have the PSS, the MIB, and so on. Then you have the other reference signals. There are about 8 types of reference signals. And this does not include the first 1, 2, or 3 symbols that are the control areas. This only includes the remaining symbols. And you will see later, well, in release 12, the issue in the control area is so critical that they are allowing now to use part of the data area of the PDCCH to send control information mapping. Well, here we are repeating the table. Now, the way we allocate those transport block groups is there are several allocation types. Okay, so what I mean by allocation is the way the DCI will map the information in the okay, is the way the DCI will map the information on the resource block groups. So it can do direct mapping in the downlink. Well, just using bit mapping, you know. I have 25 resource blocks. I said 10001, 10001, so I know which ones are being used for the UE, and then of course it will scramble the CRC with the name of the each one, and the UE will be able to recover the allocation. But this didn't provide enough diversity, because for the whole subframe the use was the same. So what they said, well, let's create another allocation type that now we divide this in 2 subsets, and those 2 subsets are shifted, the slots are shifted, and consequently we will get some diversity. and this is something that in the strategy the user will have to define which diversity mode will be used. Some of them are defined also by the transmission. Not some of them. Which ones can be used is defined by limited by the transmission system. Then there is a number 2 allocation type, contiguous, and number 2 distributed. Again, the idea here is to provide diversity and bit scrubbing. So instead of using a map, well, maybe I can have just a start and an end, and if I have, that's why it's called contiguous. I said it starts in RBG 12, it finishes in RBG 20, but to declare start and stop, I will lose some bits. So they combine start and stop into one single number called resource indication value. So they can save 1 bit there. In distributed, now it's the contiguous that was not giving enough. It was saving bits in comparing to the bitmap, but it was not giving any diversity. So they created a allocation type 2 distributed now. And the distributed, basically what it does, it breaks it maps, it has a special mapping that it maps lines and columns and so on, and it basically makes some kind of distribution of the resource block group's usage, and it's called resource block virtual allocation. So it has the logical allocation, and then it has a virtual allocation that follows a certain table specified by 3GPP. In the uplink, there are even more allocation types. So we have time 0, that is non-hopping. It's also a start-stop using a RIV, resource indication value. Then I have the time 0 hopping. Is not really the hopping that we would expect. It's a much simplified hopping. It basically hops between 2 slots, slot A and slot B in the subframe. So it's not, and this is type 1. Then we have type who hopping that is a little bit more sophisticated, and the RLC specifies where the UE should hop. There is a table for it also. And then we have type 1 that also only appears more recently in release 10, and it provides more and more diversity. So we can see clearly here that the decision of using SC-FDMA was really a little bit problematic, and that not using permutation was even worse. So they are trying to compensate this with the new releases and trying to add diversity, and also the decision to use reusable 1, they are trying to compensate this in the control channel by providing more repetition and so on. Well, how does the ENB decide what modulation and coding scheme to use, and how does it inform this to the UE? Because the UE doesn't decide what modulation scheme it will use. Who decides everything? Downlink and uplink is always the ENB. Well, the only thing the UE does is says, look, I can contribute, and I will measure and estimate the channel quality index, and I will tell the ENB, you know, in my opinion, what by telling a single number, I will tell the UE what is the modulation and the coding rate that should be used, that I believe will be good enough for me. Well, the ENB receives those measurements periodically, and of course those measurements are eating bandwidth. It analyzes the measurement, and it may consider it or not. The ENB has full control, because you will see, as you saw in the webinar number 4, those measurements on the UE are not very precise. They have variations, absolute variations of plus or minus 8 dBs and relative variation of plus or minus 4 dBs. So really, it is an indication, but it's a very gross indication. The eNodeB will rely much more on previous experiences. So I already sent it, it didn't pass, I will be sending again now with a better one. Oh, now it did pass, so it will stay around this value. It doesn't matter what the UE is telling me. So the amount of measurement the UE does is one of the parameters that has to be dimensioned. So putting too much measurement may not help any because the UE will disregard it. It will use it up to a certain extent only. So you don't need to specify excessive measurements because it will be eating your throughput. Just to compare, for control messages, the UE uses, remember they had 4 formats, the UE now, the eNodeB, we had 4 formats. This is what we call bits per symbol of those formats. So format 0 has a bit per symbol of half a bit. Format 3 has 0.07 bits per symbol. So let's compare now this with the modulation encoding schemes used by eNodeB. eNodeB defines, 3GPP defines 29 modulation encoding schemes. So each one numbered from 0 to 28, and each one defines the modulation and the spectral efficiency. What I did here, I calculated here the equivalent repetition, and I calculated here, I am presenting here the Gaussian channel required SNIR. Not Rayleigh channel. Rayleigh channel is much more. Okay, this is Gaussian channel. So now let's compare 0.234 to 0.071. So here MCS 0 sends 0.2 bits per symbol, while here we are sending 0.071. Even in the best case, we are sending 0.569. That is more or less equivalent to MCS 4. So in the control part, the best modulation MCS used is less than number 4 used in the user part. Why? Because in control part, the 3GPP does not provide any mechanism to avoid interference. While in the traffic part, the 3GPP does provide some indirect mechanism, like ICIC, like a possibility of a scheduler does implement reuse, and so on and so on. So that's why for the traffic part, the modulation schemes are much less. We have even here that uses 5.55 symbols, bits per symbol. So we go from 0.2 to 5. There is a variation here of 25 times in capacity. That's why the capacity of an LTE cell can vary 1 to 25, depending where you are and what you are using and how it is designed. And that's why the design is so important, because if you don't design it properly, you will be operating here. If you design properly, you will be operating here. Okay, so that's why it's very important. I have to speak a little bit about downlink power allocation, because this will appear later on in one of the parameters. LTE allows a small power boost in the downlink for some signals. I will not go in many details here, but basically it defines energy per resource element. And generally the symbols carrying reference signals can have a power boost that is defined by PA, and the other ones, because this one have a power boost, the other symbols that are the other reference elements, resource elements that are in the same symbol will have a power reduction called RB. And the power elements that are not where there are the symbols, they will have an average value. And this is illustrated in this figure. And here we have what 3GPP specifies for power boost is the value of PB, and it can be 0, 1, 2, or 3. And this will be that is signaled in the system information message. That's where it's sent. So let's go now to, now we have all the basics. Well, this is the last basic part that we need to know to understand the traffic allocation procedures. You probably heard about, we certainly heard about those names: radio resource management, radio resource controller, PDCP, MAC, and PHI. Here I have a very interesting diagram, because I am showing here the different layers, but contrary to the majority of the publications and books, I show both at the same time, the eNB and the UE, because the processes are slightly different between the eNB and the UE, and I have really to show them both together. So the UE and the eNB, or the network, they interchange two types of messages, what we call signaling or non-access stratum messages, or what we call data or access stratum messages. And those messages, the UE speaks, the non-stratum messages, it speaks with the eNB and with the MME, while the data messages, they go to the SGW, PGW, and then to the TCP/IP network and so on. Also, there is one element called radio resource manager that really actuates over all the different protocol layers. So imagine this as being a processor that sends information to each one of the protocol layers and gets information from each one of the protocol layers and processes it. And this also exists on the UE side, although the functionality is totally different. This one is a kind of a slave of the master that is in the eNB. Okay. Also here I indicate the layers if we compare to the OSI layers and so on. So let's see how things work. Basically the eNB sends a frame with synchronization signals that allow all the UEs to synchronize to it. Then it sends a master information blocks that basically gives the organization of the frame. And then it will send system information blocks, SIBs, that tell the UEs information about the access, how the UE should proceed to access the network. The first layer that we will analyze is radio resource management layer. So this is the layer here. In reality, it's a cross layer. The radio resource manager is the one that schedules the packets, the IP packets received. It will look at the packet, it will analyze what is the protocol this packet was sent, it will try to classify this packet according to QoS level, and it will place it in QoS queues, QoS class identifiers, so the packets are placed in queues, and also inside the queues they have priorities. So based on this, after this is placed here, a scheduling queue is released, and this queue then will be sent to the next level, that is the radio resource controller. The radio resource controller is this level here and here. So the radio resource controller, basically what it does, it handles all the NAS messages, and it also will do the check the reliability of the packets received and so on and so on. It will do also the ARQ. Now, it also handles the RRC messages. RRC messages, like the SIB message, they are encoding using a special language called ASN1, that is an abstract system notation 1. So to understand those transmits, we need to understand this language. After the RRC, things go to the packet data conversions protocol. This protocol, it's here, and basically what it does, it basically acts on the IP packets only, and the only thing it does here is to remove or replace the IP header. So what happens is that the IP header is very, very large and is very repetitive. So it has 48 or 40 bits for IPv4, 80 bits for IPv6, and it's repeated every packet, but the information is exactly the same. It's not needed for the rest of the wireless network. The only thing is the number of the packet. So basically it replaces the header, it sends the header once, and then it replaces the header just by the number. So the UE, and when it receives the packet, it can be able to reconstruct. The same thing when the UE sends a packet, each PDCP will send only once the packet, the PDCP header full, and then it will send only the changes in the packet numbering, and the PDCP at the ENB will reconstruct it. The next layer is the MAC layer. And the MAC layer, oh, I forgot the RLC layer. I have to apologize. I really forgot to include it. Well, basically the RLC layer, what it does, it will break the packets. No, it will not break anything. It will verify if the information is coming in the correct order. Because you will see that the other layers, the lower layers, they will break packets. And what can happen is that a packet may arrive without all its components. So the RLC will hold this packet there until all its components arrive. It will build the packet and then send the packet out. Okay, the MAC layer. The MAC layer basically will receive the PDCP packets, and it will build them, rebuild them. Here are the PDC packets, and basically what the MAC layer has is that it will receive from PHI an information. Look, I have an opportunity to send data that has this amount of info, that I can take this amount of information. So the MAC can take 3 or 4 packets like here and send, suppose, the end of this packet, 2 entire packets, plus the beginning of the next packet, and build one, that's the RLC, build one RLC packet. And this packet then will be sent to the MAC. And the MAC will add here the MAC header, and the MAC can pack several RLC packets in one single MAC message. Well, this is great. It looks very efficient. The problem is that you need to have several packets with the same destination. Well, you can have several packets with the same destination if those packets do not require a real-time processing. But if they require a real-time processing like streaming or voice, then you probably will have just one packet and you will not be able to do these tricks. Finally, the physical layer, probably the most difficult now to understand because of the bit scrubbing principle used. So this is the last layer. And in this layer, basically what we have now is that, again, we need to understand the frame organization. I will not repeat. We need to start with transmission modes. So remember that I said that the UE and the ENB, they negotiate transmission modes. Well, those transmission modes are here. And you can see here, suppose if mode 1 was selected, there is only one antenna. But if mode 5 was selected, well, there is transmit diversity and multi-user MIMO. So either the UE is in condition of using multi-user MIMO or it will use transmit diversity. So that's why you have in a transmission mode more than one transmission mode. Okay, and then this is mapped to a DCI formats. And those formats then define really how the information will be mapped and so on, and how many antenna ports are used. And you have for the UE, you have only 2 transmission modes. I think now in release 12 we have a 3rd transmission mode. So basically the UE, in the mapping we define the transmission mode. Based on the transmission mode we define the DCI that we'll be using. Based on the DCI we define the PDCCH with the repetition and the PDCH format coding rate and the number of channel elements that we need. Here I have a downlink frame, and remember the channel elements are spread in this area here. So as you can see, the channel elements are spread in this area on the top here. Okay, so in this area here, that's where the channel elements are. And the number of channel elements depends on the bandwidth and on the other overheads. So what happens is that the DCI will define, let's see if I have here, yes. So the DCI will define what is the size of, will define the mapping. Here I have for the different DCIs, and there are many DCIs defined in 3GPP, as you can see, what is the number of bits for each DCI. So depending on the transmission mode, you need to send more or less information. So what 3GPP said, oh, if this is a very simple transmission mode, I can get around with 35 bits. Or this is a very complex transition mode, I will need to send 60 bits of data in the DCI. Then you apply a 16-bit CRC, so the minimum DCI you have is 41 bits. The larger one you have is, I believe, close to 70 bits, 69, 59, 64, 66, that's the larger one. So based on this, then we will apply a PDCCH format. So we will spread this 41 to 66 bits according to this spectral efficiency. So I will analyze what how much redundancy I have to add and what is the spectral efficiency. On the right-hand side table here, I put several coding rates, what the equivalent repetition is, and what is the signal-to-noise ratio gain given by the repetition. So what it means, suppose if I have a UE that has an SNR that is minus 5 dBs, and I know that I need to have to detect the signal a plus 5 SNR, so I will need to choose a SNR gain of 10, so I will need to use a coding rate of 0.1, and I go here and I have 0.1, I probably will need to be here, okay, so if I am using DCI2. So that is the kind of tricks that are used to, but if I'm using DCI1, I probably will need to use 0.071, that is the lowest one. Okay, so on one side, DCI defines the mapping, and I know now where the information will be placed. But before the DCI defines the mapping, it needs to know how many resource block groups it has to allocate. So we start with the transport block. The transport block is what comes from the MAC. So the MAC can have a very large transport block. This, if it's very large, it will have to be broken in code blocks of 654 bits. But if it's not large, it will not use the code blocks. The transport blocks adds a 24-bit CRC. Each code blocks add another 24-bit CRC. Then 3GPP does another bit scrubbing trick here. Instead of telling what is the size of the transport block, it tells you an index. So it combines the MCS with with an index that will tell you, look, for this MCS, you will need to carry this transport block. You will need to carry. You will need to use so many transport block groups or resource block pairs. Again, the same mistake. Okay, so many resource block, and this will define your PDSCH format, your transport group allocation, your code words, and finally the DCI mapping. So it's a very elaborate process to save some bits, but it does work. Here again, this is the MAC transport block you can see here with the CRC of 24 bits. Phi breaks it in coding blocks with 24 bits also, and this then goes to a modulation and coding scheme table, and this modulation and coding scheme table is mapped to a TBS index. It's a one-to-one mapping. So here's the modulation order, how many bits, and there is a different mapping for downlink and uplink. So what we do next is that this table is published by 3GPP. It's a humongous table. It has 27 lines, but it has 100 columns. And basically what it does, you say, well, I need to use modulation scheme X that corresponds to TBS index 12. And I need to send 1,200 bits. So you go here and you read how many resource blocks you need to allocate. Then you go and you allocate the corresponding number of resource block groups. Okay. Well, and with this then the DCI chooses a mapping scheme, mapping format, DCI format, and it allocates one of its formats, those bits. So DUE, it doesn't receive how many bits were sent. What it does receive is the TBS index and the mapping. By the mapping, it calculates the number of resource blocks, and by the TBS index, it calculates how many bits were sent. So it's an indirect calculation again. So to finalize this part of the downlink, I would like to do a summary. So we need to do physical cell ID, 28-bit or 20-bit. We need to do a planning for PCI, for PSS, for SSS, for cell reference signal, and for uplink group. So all of this is planning of the PCI. On the downlink dimensioning, we need to dimension the number of control symbols, 1, 2, or 3. We need to dimension the number of ACNAC quadruplets. All of this is based on packet size. See how packet size is important. 1, 6, 1, 2, 1, or 2. The tool can do a lot of this for you automatically, of course, if you specify correctly the user specification. The number of control channel elements, that's the calculation that we already did in the overhead, as you've seen before, and the user traffic, the number of RBG groups that which user will be used based on its tonnage, not its throughput. Well, we finished the downlink, and we are 3 hours away, so uplink is more or less the same size. So what I will propose here that we stop here, and we continue on the September 17th, we will send you a reminder to do then the uplink. Christine, any questions here? Christine?
Sorry, I think I was muted and I didn't realize that. I have one comment, and I know you're short on time, so just one question. We'll get to the others by email. The one comment is when you mentioned ASN, I think you said abstract system notation, and it should be abstract syntax notation. So.
You're right. You're right. Pardon, it's my fault.
Yeah, no problem. Just figure I'll mention. And then just one question. You mentioned that in the transmission mode, that the transmission mode is adaptive, but also then you said that it's agreed at the UE registration. So when is it adaptive? What did you mean by being adapted?
Very good question. Oh, good. Okay. Okay, let me find the transmit mode table. Yeah, here it is. Okay, basically what is agreed is what will be used, 1 to 9 and 1 to 2. So suppose we use the UE and ENB agree on 3 and 1, or 3 and 2. Let's make it more complicated, 3 and 2. So basically what happens now that what is 3? Transmit diversity and open loop spatial multiplexing or transmit diversity. And here is single antenna port closed loop spatial multiplexing. What happens? If the ENB, and that's where the adaptive comes, if the ENB, it depends on the type of message being exchanged. If it is a broadcast message, of course it will be transmit diversity. If the UE is in a bad spot in terms of RF channel, it will be transmit diversity. But the fallback, if it moves to a good spot, the ENB will try to send open loop spatial diversity. It will not send multi-user MIMO or beamforming, okay, because the UE cannot guess what the ENB will send. So basically, you can do an RLC reconfiguration if you want, and then you say, okay, now we are not 3 anymore, now we are 9, so we will have now beamforming. But that requires an RLC reconfiguration. But the adaptation is depending on the type of the message, and if you can use the strongest MIMO or the weakest MIMO, or if it is a message that requires to be sent with the weakest MIMO, because you have to receive it, be sure, doesn't matter which kind of MIMO is used. So that's the adaptive part.
Okay. So, Leonard, with this, I think we'll conclude today's, and then we'll leave the uplink for September 17th. Just a note for everybody, the session today has been recorded and will be, you'll get a link for downloading the session. And also, the continuation on the 17th will be recorded as well. So if by any chance you're not able to attend live, you will receive as well the recording for that session. I'll leave the session open still if you want to send any more questions by the chat box so we can follow up by email later, or otherwise just wait for the links and then you can watch it again at home later. Leonard, do you have anything else to add?
No, I just would like to thank everybody, and we will continue then on the 17th. Thank you so much.